Good morning. Today we will be talking about Introduction to Hypersonic Flow. A lot of the material I am giving here is from two textbooks from Anderson. The first one is Anderson's Aerodynamics that we normally use in our undergraduate courses. You could find PDF versions of it from Amazon and also directly from McGraw-Hill. If you purchase an older version of PDF, it'll be very, very inexpensive. You could also go to other sites such as half.com and get half-price books. Georgia Tech Bookstore would also have several copies of this book, both used and new, especially after drop date for 3030 undergraduate aero. You'll find many copies of this book lying around. There's also a graduate book that Anderson has written called Hypersonic Aerodynamics. So I'm compiling some of the information from these two sources and also adding some of the other sources. So this is just a quick introduction to hypersonic flow. Then we'll have several lectures following some of the detailed features of hypersonic flow. So it's a very, very broad topic. Nobody can quite say where is the hypersonic flow starts. Is it Mach number 3 or Mach number 4 or Mach number 5? How high can it go? It's a very, very large range of Mach numbers are classified as high Mach number hypersonic flow. But one thing we know is that because of the high Mach number, the standoff distance between the body's windward surface, that means the surface that is facing the wind, oncoming wind, and the upcoming stream, the shock wave and the body is very, very small. It's a very, very thin layer, so we call it a shock layer. So the region of the shock wave and the region behind the shock layer must be carefully analyzed to estimate what's going on in the boundary layer over the body, how much skin friction it is generating, how much heat it is generating, how much of that heat is flowing into the body surface. So this is very, very important. You may remember some of the space shuttle accidents are attributed to the very hot gases generated between the shock wave and the body somehow entering into the structure because there was a structural defect and causing the explosion of the space shuttles. You may have also seen the movie Apollo 13 where because some of the thermal protection was failing, they were worried that these hot gases will enter into the structure and destroy the occupants. So here are some of the features of hypersonic flow. As we first talked about, the shock layer is very, very thin. In homework number 3, you have been doing conical flow. So where you're given a theta of the cone, and you're iteratively computing the beta of the shock wave. And in this case, you could see if the Mach number goes to very high, like 36, the angle between the shock layer and the solid wall is very, very thin. So within a 3-degree angle, lots takes place. Very high temperature, highly slowed flow, boundary layer, and the inviscid flow behind the shock wave kind of merge. It's very hard to separate where does the viscous flow end and where does the inviscid flow begin. Apologies for the typo here. It should be inviscid flow. So our conventional approach we have always used of solving only the inviscid flow and saying that the viscous flow can be handled separately by boundary layer theory may not work when the body is so close to the body surface. So this is one of the aspects of hypersonic flow. The second aspect of the hypersonic flow is that because the shock is curved over, especially for blunt bodies such as re-entry vehicles or a blunted cone in the case of a re-entry missile, behind the shock wave, the flow may be non-uniform because the shock angle, beta, is different. We studied in our conical flow that the conditions behind the shock wave depend on the shock angle beta that it makes, and therefore different turning angle will occur, different layers of slowdown will occur, entropy jump will be different. Therefore, behind the shock wave, you get changes in the entropy. So as the fluid particles travel from leading edge towards the trailing edge, they carry this entropy information with it. Entropy is transported by the fluid particles. So all over here, you get an entropy layer, which is a non-uniform entropy layer. We also already know that there is a boundary layer. Normally in viscous inviscid interaction problems, we will say outside the boundary layer is inviscid, inside the boundary layer is viscous, and we will kind of look at the slope or the vorticity to determine where does the boundary layer edge occurs. But here, because of the entropy and the non-uniform velocity, it's very hard to tell where does the boundary layer end and where does the outer rotational flow continues. So this becomes a problem when people started modeling analytically or computationally the flow, hypersonic flow over blunt bodies. A third issue is the boundary layer is very, very thick. We have studied in undergraduate aerodynamics that for a laminar flow, the boundary layer thickness is proportional to 1 over square root of Reynolds number. So if the Reynolds number is 1,000,000, 1 over square root of 1,000,000 is 1,000, 1,000th of the body chord. So if the body chord was 1 meter, this is less than 1 centimeter. It's like a 0.1 centimeter boundary layer thickness. But in hypersonic flow and compressible flow in general, we create a lot of heat in the boundary layer. Kinetic energy gets converted into temperature, so you get a temperature layer. P equal to rho RT. So when the temperature increases, rho decreases. Pressure is roughly a constant. When density decreases, you need a bigger area. Rho times velocity times area is the mass flow. So the boundary layer tends to be much thicker in compressible flow. So in hypersonic flow, the boundary layer is very, very thick. So our conventional assumptions that the boundary layer is very thin, may be neglected, and we can first solve the outer inviscid flow does not work. We need to add the thick boundary layer thickness to the body surface to come up with an equivalent body and then analyze that equivalent body with the inviscid flow technique. So we would need some kind of a viscous inviscid interaction where the outer inviscid flow, which determines the pressure distribution, is coupled with inner boundary layer, which determines the boundary layer thickness and therefore changes the effect of the effective body surface that is shown in here. The next thing we have to worry about is high temperature effects. During re-entry, let's say this is, for example, is the lower surface of an Apollo 11 re-entry module as it entered the Earth's atmosphere. The Mach number is 36, very, very high. So behind such a high Mach number flow, the shock wave produces tremendous amount of heat. So you produce, in this case, for example, 11,000 degree Kelvin. All of this heat goes into the molecules. So molecules, you may remember, most of them are diatomic molecules. For example, they may be nitrogen atoms, 2 nitrogen atoms forming a nitrogen molecule, or 2 oxygen atoms forming 2 oxygen molecules, etc. So when you have such high temperatures, all of it goes into the internal energy. The internal energy does several things. First, linear motion of the molecules increases, random molecular motion in the left to right, bottom to top, and also up and down and perpendicular to the plane of the paper. So the molecules, for example, may go left to right, they may go left to right, bottom to top, and they may go in and out of this plane of this paper. So when those things occur, energy goes into this. So that's one part of the kinetic energy. The molecules may start rotating more rapidly, so rotational kinetic energy becomes very high. The molecules may start vibrating. That means the 2 atoms may want to move apart from each other, but the intramolecular attractive forces, the protons inside one atom, one nitrogen atom, maybe attracting the electrons of the another nitrogen atom. They try to keep it together. So you get some kind of a spring mass system where the two atoms want to vibrate. This is called a vibrational degree of equilibrium. So some of the energy goes into vibrational energy. But you may also get a dissociation of the molecules into atoms. And the atoms may have outer layers of electrons may be stripped off. The atoms may become ionized plasma. So this region may be a plasma, a soup of positively charged ions and negative electrons floating about. And also, because you have such high temperature, you may have a radiative heat that goes out into the outer flow. This is how we see a re-entry vehicle, because you see the radiated heat from the bottom of the re-entry vehicle. But some of that radiated heat can also go towards the surface. So you have to protect the surface from the extreme heat radiated by these hot gases towards the surface. Here's a picture of a re-entry vehicle. As a re-entry vehicle increases, at low Mach number, we can assume a calorically perfect gas. That means we can use T0 equal to T times 1 plus gamma minus 1 over 2 times Mach squared. Cp times T0 equal to Cp times T plus V squared over 2. We can assume the Cp is a constant. It's not even a function of temperature. So it's called a calorically perfect gas. But as the Mach number increases, we have to assume that the specific heat Cp and Cv are functions of temperature and possibly the functions of temperature and pressure. So therefore, a different thermodynamic model will be needed. Notice that the temperature is not getting quite so high at certain Mach number, because you have now more degrees of freedom, not just the linear degrees of freedom and rotational degrees of freedom. You have vibrational degrees of freedom, dissociation, so more modes into which energy can go. Therefore, the effective temperature is decreased for real gases compared to a calorically perfect gas. Here are various vehicles: ICBM, orbital re-entry vehicles, lunar return vehicle Apollo, Mars return vehicle. Notice the extreme Mach number that the Mars return vehicle will take. So we have to be prepared for modeling these type of vehicles with the computational mechanics, experiments. Experiments are very hard to do at such extreme Mach number. So we have to come up with the effective ways of modeling such high hypersonic re-entry vehicles. Another thing that happens is, because we are at a very high density altitude, the ambient density is very low. It's possible that the molecules spread so far apart, they may be, instead of being microns apart, they may be meters apart. So if the molecules are far apart compared to the vehicle dimensions, we cannot assume a concept of continuum, which says everything is a continuous fluid. All the molecules have the same property if you sample it in a small region. We cannot assume density, temperature, velocity are all uniform for a collection of molecules. We may need to deal with the molecule by molecule. That means we may need to do a molecular dynamics analysis rather than a continuum Navier-Stokes based analysis that we have so far preferred. So this is a difficulty we face in hypersonic flow. As I mentioned earlier, high temperature effects become a problem. We can no longer use T0 equal to T infinity plus 1 plus gamma minus 1 over 2 times m infinity squared. As a minimum, the gamma must be corrected. It will no longer be 1.4. It will no longer be 7 by 5. It will have to be a different number. By the way, inside the boundary layer, the temperature is also affected by the Prandtl number. For laminar flow, the Prandtl number is 0.72. For turbulent flow, it's 0.8. So the square root of 0.8 is roughly 0.9. So the temperature at the wall in viscous flow is lower. Again, this gamma can no longer be treated as a constant. We'll have to treat gamma as a function of temperature, possibly a function of temperature and pressure. So common engineering practice is, as a minimum, have a curve fit for gamma as a function of temperature and use this curve fit. Professor Stephen Ruffin in our school has done a lot of work in modeling CP and CV at extremely high temperatures. His thesis work is a great work of art. So in summary, hypersonic flow has got several features that we need to worry about. High temperature effects. We have to worry about gamma as a function of temperature or a function of temperature and pressure. You may wonder, what does the pressure have to do with it? If the pressure is very high, it may mitigate dissociation. Molecules may not want to dissociate into atoms. Atoms may not want to dissociate into positive ions and electrons. So pressure may become a problem. The word non-equilibrium flow means the time rate over which these changes occur may be the same as the time rate for the flow to go from point A to point B, in which case the time scales associated with the flow is same as the time scale it takes for the gases to dissociate and ionize and so forth. If this is happening very, very fast, a fast chemistry, then we can assume that immediately behind the shock wave, all the dissociation, all the changes to gamma have occurred, then we can use that gamma. On the other hand, if the dissociation, ionization is taking place over a period of time, and if the molecules are also being convected, moving about during that period of time, then we have to assume everything is non-equilibrium. We mentioned that the shock waves is very close to the body. Stand-up distance is very, very low. We said that the entropy layer may merge with the boundary layer. So it's not clear what to apply as the boundary condition to the boundary layer because the entropy layer is also non-uniform. Boundary layer is extremely thick. Therefore, the body shape looks like this dotted line rather than this solid line. So we cannot do an inviscid analysis of the original body shape. You'll have to do an inviscid analysis of this modified body shape, which includes the original body plus the thickness of the boundary layer. We mentioned that at high altitudes, molecules may move not as a continuous fluid, but as random molecules. They may bounce off the surface. They may travel close to the surface at high slip velocities. We have always used a no-slip velocity boundary condition in viscous flow, saying that the flow sticks to the surface. So at the surface, the molecule has the same velocity as the surface. This may be violated. So hypersonic flow has got numerous features that we have to worry about. So in this lecture, we are going to get some simplified estimates of lift, drag, and pitching moments. In earlier lectures, we used to do for subsonic flow, Prandtl and Glovert, Common, CN, and Lighton. For supersonic flow, we used to do Acker's theory. We said Lyman transonic flow is nonlinear, so these theories break down. In hypersonic flow, these theories also break down. So we don't have these simple theories that we can apply in hypersonic flow. Fortunately, there are some approximate estimates in hypersonic flow that we could do. So we are going to cover those in the rest of this presentation. The very first model, not surprisingly, was done by Newton. This was done almost 300 years ago, now probably more like 350 years ago. Newton had already developed his equations of motion. So he thought the air molecules are nothing more than solid particles such as a rock or a stone or a falling apple. A object in motion will continue to travel along straight lines, maintain its momentum, unless something happens to change its direction, such as a force or a collision with another particle or collision with a solid surface. So Newton said, I'm going to model fluid dynamics. He didn't know about hypersonic aerodynamics. He thought all fluid dynamics. I'm going to use my Newton's equation of motion of the particles. So he said all the particles travel along a straight line until they hit the solid surface. but they go through an inelastic collision. That means it's like a rubber ball that's got not much air inside. So when it hits the surface, it does not bounce back. What happens is it loses its normal momentum, but the tangential momentum tangent to the surface is preserved, so the particle continues to move in a direction tangent to the surface. So think of a jello that you throw against an inclined wall. When it hits the wall, it's not going to bounce back. It'll come to a stop in the normal direction, normal to the wall, but it'll continue to slide down along the surface. So this is the model that Newton proposed for all fluid mechanics. He didn't know subsonic flow from transonic flow from hypersonic flow. This is several hundred years ago. So he was treating all fluid particles similar to solid particles. The only variation is they lose their normal momentum, but they retain their solid momentum. So the collision is inelastic rather than elastic. So if you have, for example, a flat plate at an angle of attack, our incompressible flow theory will say Cl equal to 2 pi alpha. Our Acker's rule will say Cl equal to 4 alpha divided by square root of m infinity squared minus 1. Now Newtonian model will say when a particle comes towards a body, when it hits the surface, it'll lose its normal component of velocity normal to the surface, but it'll keep the tangential component of velocity tangent to the surface, so it'll slide along this surface. So if this is the v infinity that the particle has got as a velocity, if the body is at an angle of alpha, then it'll lose the v infinity sine alpha component of velocity, but it'll retain its v infinity times cosine alpha component of velocity. So this is what Newton model. It's far from a perfect model, but this is the model he assumed 300 plus years ago. So let's take a small area delta A on the surface. So consider small delta A on the surface. How much is the flow entering a control volume normal to that surface? Delta A times h. The flow velocity will be rho infinity times the normal component of velocity v infinity sine theta times the delta A. Density times velocity times area would be the momentum entering the control volume. As the fluid enters that control volume, it brings in the velocity normal to the surface of v infinity sine theta. Therefore, if you multiply the mass flow rate by this velocity, you'll get the momentum flow rate. So you'll get to rho infinity, v infinity squared, sine squared theta, delta A is the rate at which normal momentum is entering our control volume. So think of a control volume as a small box normal to the surface. The box area where it touches the body is delta A. So density times velocity squared times delta A is the normal momentum, where the velocity squared is v infinity sine theta squared. So upon impact, all this normal rate of change of normal momentum gets converted into a pressure over and above atmospheric pressure or an excess pressure, which we normally call a gauge pressure, which is this rate of change of momentum per unit area. Pressure times area is a force. So this is the force. If you divide it by area, then you get this. Therefore, according to Newton, surface pressure coefficient, he didn't know surface pressure coefficient, but this is a later definition during the late 19th century and the 20th century, is the gauge pressure divided by 1/2 rho infinity v infinity squared. So from Newton's theory, we get a Cp of 2 times sine squared theta. How about this is called the windward side. So this is what happens on the windward side. How about the other side? We call the shadow region, we call it a leeward side. So in that region behind the flat plate, nothing happens. According to Newton, P equal to P infinity, Therefore, the gauge pressure behind the body on the other side of the body is 0. Therefore, Cp is 0. So on the windward side, Cp is 2 times sine squared theta. On the leeward side, or the shadow side, Cp is 0. So this is what Newton's model will produce. Cp is a modern definition. Newton was thinking only of equations of motion. So for example, if you have a re-entry vehicle like a missile entering atmosphere, all the molecules, when they hit it, you'll have to first find the normal component of velocity. You could do v infinity times dot n. This normal vector is normal to the surface. So if you have a CAD representation of the surface, you can easily find the unit normal vector. So once you know the unit normal vector, you can do v infinity dot n by v infinity. So that's what he would use to compute the pressure distribution all over the front body. In the back part of the body, he will assume that this is a shadow region, therefore Cp is 0. So we know the pressure distribution on the windward side, we know the pressure distribution on the leeward side, so we could integrate it to compute the lift, drag, etc. So this is the Newtonian model. So this is what Newton came up with. By the way, a lot of these things Newton was doing when he was given a long vacation from Cambridge University because of the plague. Just like we are having coronavirus and people are asked to go home, all the students from Cambridge had returned back to their home. Newton was taking a nap under an apple tree. That's when he came up with the theory of gravitation. He also developed this fluid mechanics theory at the time. A lot of the later theories, such as the Kepler's law, Newton had already formulated. He had developed his own version of calculus, differential equation, how to integrate, and so forth. So all the difficulties we have with our mathematics, you can squarely blame it at the feet of Newton. So what's wrong with Newton's theory? It's very, very simple, very beautiful, very elegant. Makes a logical sense if you view the fluid particles as discrete particles that don't bump into each other until they strike the surface. But it's also very, very wrong because particles do bump into each other. They change their trajectory long before they hit the surface. Therefore, we cannot use Newtonian theory in subsonic flow, transonic flow, or supersonic flow. Here is a picture of the potential for a cylinder we had done. Notice that the particles start deflecting long before the body. How did the body know when to deflect? Because the high pressure that's generated at the body leading edge, in this case the stagnation point, whenever there's a high pressure region, the flow wants to avoid it. It wants to go towards a low pressure region so that this turning takes place. So this is what happens in subsonic flow, transonic flow, even in supersonic flow, considerable turning takes place upstream. However, in the hypersonic flow, because the shock is so close to the body, the particle does not know the body exists. So as soon as it crosses the shock wave, it's got very little real estate. It has to turn immediately and start following the surface. So the inelastic collision that Newton talked about, the particle hits the surface, then starts following the body, is quite valid for hypersonic flow. So Newton's theory works for hypersonic flow. It does not work for subsonic flow or transonic flow or supersonic flow. So some people came up with a modified Newtonian theory that slightly improves it. So basically they said rather than using a Cp equal to 2 times sine squared theta, I'm going to compute the pressure, stagnation pressure behind the shock wave. Then I will use the Cp as stagnation pressure behind the shock wave divided by minus static pressure in front of the shock wave by 1/2 rho v squared. This is at the stagnation point. This is the maximum value of Cp. Everywhere else I will use, instead of a 2, the Cp max times sine squared theta, where again the theta is the angle between the streamline and the body surface. At the stagnation point, theta becomes 90 degrees, so this becomes 1. So this is called a modified Newtonian theory. So the modified Newtonian theory works fairly well, especially for bodies of revolution. Here it's a parabola that's rotated about its axis of symmetry. You get a paraboloid. Here is the distance from the leading edge stagnation point over the upper surface of a parabola, or for that matter, lower surface, because it's axis symmetric. Say P naught is the maximum here behind the shock wave. Then the pressure starts decreasing. So this is what we get from a modified Newtonian theory. This is from the CFD. It agrees quite well. So modified Newtonian theory is often used for blunt body in re-entry. We are now going to apply the flat plate theory to Newtonian theory to a flat plate. This is from a book by Anderson, Subsonic Aerodynamics. So it's from the chapter 14. So we are going to take a flow coming at an angle of attack. We know that the Cp in the lower surface is 2 times sine squared alpha, because alpha is the turning angle. So there's 2 times sine squared instead of theta, it's 2 times sine squared alpha. On the leeward side, Cp naught is 0, so we know the pressure difference. So you could integrate the pressure difference along this distance to find the normal force. Once you have the normal force, you could take a lift component and you could compute the drag component. So let's do the algebra. This is 2 times sine squared alpha. This is 0. So this is a constant. Bring it outside. Integrate all over the body from the leading edge of the flat plate to the trailing edge of the flat plate. So this is the normal force. Once you have the normal force, you could divide it into lift force, because this is Cn. Cl will be Cn times cosine of alpha. Cd will be Cn times sine of alpha. Opposite side, hypotenuse. So if you do that, then you get Cl equal to 2 sine squared alpha times cosine alpha. Cd equal to 2 sine cube alpha. L over d equal to cotangent of alpha. Notice that if you have an alpha of, let's say, 10 degrees, alpha in radian will be roughly 0.1 radian. So cotangent of 0.1 will be cosine of 0.1 in radian by sine of 0.1 in radian will be roughly 10. On the other hand, if your alpha was, let's say, equal to 20 degrees, then you're going to get 1 over 0.2, which is 5. So L over D in hypersonic flow is much lower than L over D in subsonic flow or transonic flow. So here is a worked out example for a thin flat plate at an angle of 15 degrees at Mach 8 flow, straight out of Anderson. So we're going to do it 2 ways. One is by using the shock wave theory and the Prandtl-Meyer expansion. On the lower side, we are going to assume the shock wave. On the upper side, at the corner of the leading edge, we are going to assume that the flow goes through an expansion. So you put the shock wave here, find the conditions behind the shock wave. We have already looked at the oblique shock relations. We know how to find the pressure behind the shock wave, Cp behind the shock wave. Prandtl-Meyer expansion, we did not cover in detail because it's an undergraduate flow concept, but you can find the Mach number behind the expansion, therefore the pressure behind the expansion. So if you do go through that type of an approach, we get the conditions behind the shock wave. So this is the Cl, you get 0.20 and 0.05. This is at 15 degree angle of attack. So L over D is 3.73, which is very, very low. Pardon me, this is, you get 3.73. How does a Newtonian theory do? You get a Cl 2 sine squared alpha, 2 sine squared Cp is this, Cl is this number, Cd is this number, L over D is 3.73. So at Mach 15, we get reasonable answers. Here it is seal is 0.20 from the exact theory. Here it is 0.1293, 50% off. CD is 0.05. Your CD is 0.034, again 50% off. Both of them are 50% off. Therefore, the L over D from Newtonian theory is close to L over D from the shock expansion theory. But if you go to low Mach number, modified Mach number, you get even worse answers. So Newtonian theory underpredicts the CP on the bottom surface by as much as 30%. L and D are therefore affected by as much as 30 to 36%. Newtonian theory does not work so well for 2D geometries. It does somewhat better for 3D geometries, such as re-entry bodies, blunt bodies, such as the Apollo module, and also even for cones. This, for example, is a conical flow that we have studied. If you look at the pressure over the surface behind the shock wave, as the Mach number increases, Newtonian theory gives this answer. 2D wedge theory gives this answer. Our conical flow method that you have done in your homework number 3 gives this answer. Once you assume Newtonian flow theory, these numbers are fairly good. So Newtonian flow theory works for bodies of revolution, not so good for 2D geometries. So you cannot apply it on a wing of a space shuttle, but you can certainly apply it for the fuselage of a space shuttle or for a non-wing, non-lifting re-entry body. So this concludes our presentation on hypersonic flow, and we will continue to do more recording in the future.